Welcome to another deep dive. This time, we're going below the surface, way below, to explore something you may know a little about, but I bet you there's a lot more to it than you think. We are talking stalactites and stalagmites. And yes, I did practice saying that a few times before we got started today.
I think you got it. And while most folks think of caves when they hear those words, they can pop up in other places too, even some places we humans had a hand in creating.
We'll get into all of that. First, just to give everyone an idea, the research for this one really ran the gamut. We've got, let's see, articles from a couple of different rock and gem magazines. There are a bunch of science websites that have been really helpful, even found a YouTube transcript that kind of breaks things down in a pretty accessible way.
Yeah, and of course we couldn't pass up BBC Science Focus, always a good source for solid science reporting. And Merriam-Webster, gotta have those definitions nailed down, right?
Absolutely. And we even went ahead and took a look at how some creation science folks address these formations, because there are always interesting questions about how they fit into different timelines and perspectives.
Right, and to round things out, we went to the National Park Service website, some educational resources like Vedantu and Wizant Lessons, Wikipedia for that general overview, and then Science Direct for the real in-depth stuff.
Can't forget the National Speleological Society. You got to hear from the people who really know their caves.
Oh, and there's a great geology blog that we found some cool tidbits on, and good old How Stuff Works. They always manage to dig up something interesting. And of course, since we are talking about caves, Mammoth Cave National Park's website had some good details too.
So yeah, we've got a lot to cover. We are going to try and get the full picture here. Like, what are stalactites and stalagmites exactly? How do they form? Where do they form? How fast do they grow? Or maybe the better question is, how slow do they grow? And what are they made of? Oh, and we want to debunk some common misconceptions along the way because I think there are a few out there. So to start, when we are talking about stalactites and stalagmites, what exactly are we talking about?
Stalactites, those are the ones you'll find clinging to the ceiling, hanging down. You see them a lot in caves, yeah, but also places like hot springs and even some man-made structures like bridges or mines. The name itself kind of tells you a bit about what's going on. It comes from the Greek word stalactos, which just means dripping.
So dripping, like water dripping, which makes sense when you picture them. And stalagmites, those are the ones that grow up from the ground, right?
You got it. They're kind of like the mirror image of stalactites. And the name for stalagmites also comes from Greek. It's stalagmites, and it means dropping or trickling. It's pretty cool that both those words, stalactos and stalagmites, actually trace back to the same Greek verb, stalesein, which means to drip. So the name itself tells you they are both formed by dripping water.
So they're both kind of expressions of the same process, just one going down and the other coming up. Is there like an overall term for both of them?
Yeah, they're often lumped together under the term ripstone. And another thing to remember is that they both belong to a bigger category called speleothems.
Speleothems.
Yeah, speleothems. These are basically any mineral deposit that creates different formations in caves. Now, here is where it gets a little tricky. Not all stalactite-looking formations are speleothems. That is, only if they form in natural caves. If they form outside of caves, say on human-made stuff, they are classified differently. But we'll get into that later.
Okay, so speleothems are just the cave formations, and stalactites and stalagmites are the most common types of speleothems. I think I can remember that. But I'll admit, I always mix up stalactites and stalagmites. Is there a way to keep them straight? Like, how do you remember?
Well, there are a couple of memory tricks. This is the one I use. Stalactites, they hold tight to the ceiling. See, they both have a C. And then stalagmites, they are on the ground with a G and might push up with all their might.
That's a good one. I am going to use that from now on. Tight to the ceiling, might from the ground. All right, so now that we know what they are, how do they actually form? Like, what's the process step by step?
The most common way, and this is what happens in those amazing limestone caves you see, starts with just regular old rainwater. As this rainwater seeps down through the ground, through the limestone, it picks up carbon dioxide. It gets it from the air, from the soil, all around. And when the water mixes with that CO2, it creates a weak carbonic acid.
So the rainwater is becoming slightly acidic?
Right, and this slightly acidic water then starts to react with the limestone, which is mostly made of calcium carbonate. You might know it as calcite. And the carbonic acid in the water dissolves that calcite, that calcium carbonate. What you get is a solution of calcium bicarbonate.
Okay, so the limestone is essentially dissolving into the water.
Exactly. And this calcium bicarbonate solution eventually makes its way to the cave ceiling, and it starts to drip. Now, here is the cool part. When that water droplet is hanging from the ceiling, exposed to the air in the cave, a reverse reaction starts to happen. Some of that carbon dioxide that was dissolved in the water starts to escape. It degasses, and as it does, the calcium carbonate can't stay dissolved anymore. So it starts to precipitate out of the solution.
So as the water droplet hangs there, it loses some of its carbon dioxide, and that causes the dissolved limestone to turn back into a solid.
Yep, that's it. And what happens is a tiny thin ring of calcite gets deposited on the ceiling. Now, every time another drop of water comes along, the same thing happens. Another ring of calcite. And over a really, really long time, those rings build up, and they form a hollow tube. We call these soda straws because they are really thin, usually only like 4 or 5 millimeters across. And although they can get pretty long, they are very fragile.
Okay, I can picture that, like a thin, delicate straw hanging down. So what happens if one of these soda straws gets blocked?
Well, if a soda straw gets clogged, maybe by some debris or a mineral deposit, the water can't flow through the inside anymore, so it starts to run down the outside of the straw. And as it does, more and more calcite is deposited on the outside, making the stalactite thicker and thicker. That's how it starts to take on that more familiar cone shape we typically think of.
So the typical stalactite is basically a soda straw that has been coated and thickened by mineral deposits.
Exactly. Now, what about the stalagmites, the ones growing up from the ground? They are formed by the same dripping water that created the stalactite. See, when a drop of water falls from the stalactite, even after some of the carbon dioxide escaped, it usually still has some calcium bicarbonate dissolved in it. When it hits the cave floor, even more CO2 can escape. And as it does, guess what happens? More calcium carbonate precipitates out, this time on the ground. And over time, drip after drip, those deposits build up, and you get a stalagmite.
So it's this constant back and forth, the water dissolving minerals from above, then depositing them below as the carbon dioxide escapes.
Ah.
So cool. Now, if this keeps going for a long, long time, what happens?
Well, given enough time, a stalactite and the stalagmite under it can actually grow until they meet. When that happens, they fuse together, and you get a column or a pillar that stretches from the ceiling all the way to the floor. Sometimes these are called stalagnates, a combination of stalactite and stalagmite.
That's amazing, going from these little drips to these huge columns over who knows how many years. It really makes you think about how old the Earth is. Speaking of time, how fast did these things actually grow? I've always thought it was super slow.
Yeah, you are right. In a typical limestone cave, stalactites grow very, very slowly. We're talking less than 10 centimeters, like less than 4 inches, every 1,000 years. The average growth rate is something like 0.13 millimeters per year. That's incredibly tiny.
So each inch of growth could represent centuries. That's wild. Yeah, are there any conditions that make them grow faster?
The fastest growth happens when you have a slow but steady drip of water that's really rich in calcium carbonate and carbon dioxide. In those ideal conditions, a stalactite might grow as much as 3 millimeters, or about 1/8 of an inch, per year. It's still not fast, but it's a lot faster than average. And scientists have used radiometric dating to figure out that some of these formations are incredibly old, like over 190,000 years old.
Wow, 190,000 years.
Hmm.
It seems like how fast they grow depends on a lot of different things in the environment.
Yeah, the main factors are how often the water drips and how much dissolved calcium carbonate is in that water. The amount of air circulation in the cave also matters. Good airflow helps that CO2 escape, which, like we talked about, leads to more calcite deposits.
Okay, so we've talked about the ones in limestone caves, but you mentioned before that you can find stalactites and similar formations in other places too. How does that work, and is it different from the limestone cave formations?
Yeah, there are some interesting variations. One type is concrete stalactites. Sometimes they're called calthamites. These form on concrete structures like bridges, or if you have a leaky pipe in a concrete bittering. And here's the wild part. They can grow way faster than the ones in caves, like up to 1 centimeter a year, and in some cases, they've been observed to grow a couple of millimeters per day.
A centimeter a year. That's a lot compared to those tiny fractions of a millimeter in caves. Why are they so much faster?
The chemistry is a bit different. See, concrete has calcium oxide in it. When that calcium oxide reacts with water, it forms calcium hydroxide. If rainwater, or any water really, seeps through cracks in the concrete, it picks up this calcium hydroxide. Then when that solution reaches the edge of the concrete and is exposed to the air and CO2, it reacts again, and this time calcium carbonate precipitates out, just like in the caves. The big difference is that the starting point is different. Remember, concrete is made by heating limestone to make cement, and that changes how it reacts chemically.
So even though the final product, the calcium carbonate, is the same, the chemical process is different. And that's why they grow faster.
Right. And there's another difference, too. The water that forms concrete stalactites is often very alkaline, way more alkaline than the water in caves. The pH can be above 9, sometimes even above 13. In natural caves, the pH is usually closer to neutral, somewhere between 7.5 and 8.5.
That's a big difference in the chemistry.
Right.
What about those other types you mentioned, the ones formed by lava and ice?
Okay, so lava stalactites, or lavascals as they're sometimes called, form in lava tubes. These form super fast, like in hours, days, maybe a few weeks, while the lava is still flowing and dripping. Once the lava stops flowing, they stop growing. And unlike the limestone ones, if they break, they don't grow back. There are actually different types of lava stalactites, like shark-tooth stalactites. Those are broad at the base and taper to a point. Splash stalactites, which have all sorts of irregular shooks because they are formed by splattered lava. And tubular lava stalactites, those are hollow inside.
So you have molten lava dripping like water,
Hmm.
and then it solidifies into these formations. I bet they look very different from the ones you see in caves. What about ice stalactites? We all know about icicles forming outside in winter. Can they form inside caves too?
Yeah, they can. Ice stalactites, or icicles as we usually call them, form when water seeps into a cave and freezes. It can happen pretty quickly, within hours or days, if the temperature is cold enough. They can even form under sea ice, where they are called brinicles. Unlike the other types of stalactites, ice stalactites are pretty temporary. If the temperature rises, they melt, and then they can reform if it gets cold enough again.
So those are more dependent on the weather and the seasons. You also mentioned something about stalactites being made of things other than calcium carbonate. That was a surprise.
Yeah, most stalactites are made of calcium carbonate, but they can actually be formed from a whole bunch of different materials. We've already talked about lava, but there are others like gypsum, halite, which is just salt, mud, peat, pitch, sand, even something called amberite, which is crystallized pack rat pea. And in limestone caves, although most of the formations are calcite, you can also find other minerals like aragonite, huntite, and even opal. It just goes to show that all sorts of processes, both geological and biological, can contribute to these formations.
Pack rat pea. That is something I did not know. It seems like there's a lot more to these formations than meets the eye. So besides stalactites and stalagmites, are there any other cool formations people might see in caves?
Oh, yeah, definitely. We talked about soda straws. Those are like the baby stalactites in the columns. Those are the stalactites and stalagmites that have grown together. But there's also something called flowstone. That's where you get these sheets of calcium carbonate deposited on the walls or floors of the cave. It's often described as looking like melted icing or frozen
Oh yeah,
waterfalls.
I've seen pictures. It does look like frozen waterfalls.
Yeah,
There's a really famous one in Mammoth Cave called the Frozen Niagara.
exactly. And then there's halictites. Those are really strange. They are these twisting, curving formations that seem to grow in every direction like they don't even care about gravity.
Really? How do they do that?
The short answer is we don't know for sure. It seems like it has to do with how slowly the water moves through them, so slow that other forces, like surface tension, become stronger than gravity.
So cool. Anything else?
There's cave popcorn, those are these little knobby formations, and cave pearls, those are small round stones that form in shallow pools of water. And finally, there are these really delicate, almost feathery formations called cave flowers or frostwork.
So many different shapes and sizes. It's amazing. If anyone wants to see these amazing formations for themselves, where are some good places to go?
Well, you can find stalactites and stalagmites in limestone caves all over the world. Some of the most famous ones are Carlsbad Caverns in New Mexico, Timpanogos Caves in Utah, and Mammoth Cave in Kentucky. And then, of course, there are caves all over the world, like Jenolan Caves and Buchan Caves in Australia.
Are there any record holders? Like the longest stalactite or the biggest stalagmite?
There are. There's a stalactite in Jeda Grotto in Lebanon that's supposedly about 27 feet long. And then there's another one in Brazil in a cave called Gruta Rei de Mato that might be even longer. And the largest stalagmite is in Cuba in a cave called Cueva Martin Infierno. It's a whopping 204 feet tall. And then there are the columns. Those can get pretty big too, sometimes over 65 feet tall and wide. Of course, if you want to see lava stalactites, you'll need to head to a place with lava tubes like Hawaii. And ice stalactites, you can find those wherever it gets cold enough for water to freeze in caves.
204 feet tall. That is just mind-blowing. Okay, just to make sure everyone remembers, can we do a quick recap of the difference between stalactites and stalagmites? I think those memory tricks you mentioned earlier were really helpful.
Sure. Stalactites hang tight to the ceiling, both with a C. Stalagmites grow up from the ground with all their might, both with a G.
Perfect. Now it's going to be stuck in my head forever.
Yeah.
Well, this has been an awesome deep dive. It's really incredible how these formations, which look so still and unchanging, are actually the result of these slow, ongoing processes that have been going on for thousands, even hundreds of thousands of years.
Yeah, it really makes you think about geological time, doesn't it? So, just to recap, stalactites and stalagmites are mainly mineral deposits formed by water dripping through soluble rock, most often limestone. And while they grow very slowly in caves, things can speed up a lot in places like concrete structures or through other geological processes like lava flows or freezing water.
It was really interesting to learn about how the chemistry can be different between natural cave formations and those concrete ones, even though they're both made of calcium carbonate in the end. It shows you that there's more than one way to get to the same result.
Absolutely. And it's important to remember that there's a whole world of speleothems out there, not just stalactites and stalagmites. There are all sorts of other cool formations, like those crazy helictites, the flowstone that looks like frozen waterfalls, and cave pearls. Each one has its own unique story to tell.
It really makes you wonder what other hidden wonders are out there waiting to be discovered.
Yeah.
Before we wrap up, here's something for everyone to think about. We talked about how the time scales for these formations can be so different, from a few hours for an ice stalactite to hundreds of thousands of years for a giant limestone one. What does that tell us about how our planet is constantly changing, both in natural ways and because of things we humans do? And what about other things in the world that seem permanent and unchanging? Are they really? Or are they just changing so slowly that we don't notice? Something to ponder, right?
Definitely. It's a reminder that even though things may seem static, there's always something going on, even if we can't see it.
And on that note, thanks for joining us for another deep dive. We'll see you next time.
See you then.